recording here. All right. My Zoom disaster from this morning seems to be fixed. So that's good for me. Just a couple of notes. So instead of doing the normal distribution questions and the binomial questions all in one assignment, I just took them and I split them up into 2 assignments to help you kind of focus on the different types of questions. So there's assignment 8 and 9, which are both on the quiz tomorrow. Oh my gosh. Maybe this is a good time because I did have someone ask me. So remember, if this quiz doesn't go well, that's okay, right? As long as the final exam is better, I'll pretend that you didn't show up and then we'll shift it to the final exam, right? But it's better if you write it. If you write it tomorrow, try it, see what happens, but just know that if you can do better on the final exam, so overall, then I'm happy with that, okay? I did post this notes and examples for the remainder of chapter 4 because there's a lot of concepts that I want to talk about, and they are just mostly stolen from the textbook. So we'll go through that today. Okay. Even though I know there's more people coming probably. You think day before a quiz, I'm guessing. Okay, so before we do that, let me see here. Let me bring it in here. Oh, I need to set up this note. Stat 230. 9 need lines to help me out a little bit. Okay. Set the mood. 1, 2. All right. So in terms of material from today, what's going to be on the quiz is there will be a normal approximation to the binomial, which is what we're going to start with. So we're going to spend quite a bit of time here. And then there's going to be a question where you have to tell me what type of question it is. So is it a binomial? Is it a geometric? Is it a negative binomial? Is it a Poisson? That kind of thing. And so that means that we have to kind of know what all those are, right? But we don't have to solve anything. I'm not going to ask you to solve any one of those. Just tell me, okay, here's a question. What type of question is this, right? What type of distribution is this from? Okay. And I have an example of that I want to go through. Okay. So let me write that down. So on the quiz tomorrow, maybe I'll do. Right. There will be a normal approximation to the binomial. And there will be a question where you're asked to tell me what type, right, from a list of different options. Okay. So given a question,
is the first point what we did last class?
That's what we're going to start with today. So there will be a binomial question from last class, and I'll review just the formula that we landed on, right? And then today I want to talk about the normal approximation to the binomial. So gets kind of hectic. I wish we had Monday, Wednesday, Fridays, make more sense, right? Then Tuesday, Thursday, Friday. Given a question, tell me what type of distribution, I'll say. Of distribution, it follows. And I do have an example like that, and I'll tell you, this is the one that I mean. So for some review, we talked about the binomial distribution. And we said, okay, the binomial distribution helps us find the probability of some number of successes in n trials, right? And so we can find the probability that x equals k, right? Where x equals k is just shorthand for the probability of k successes. And what we developed was, okay, if we make a tree diagram, for example, and I trace down, we know that there's many ways that we could find k successes, right, in n trials. So that's why we use the n choose k function. And I will bring calculators, of course, in case you forget yours, but it might be nice to have your own that you know how to work for this. You are allowed to use R if you want to, right? So you're welcome to use R if you can work through that. I haven't shown you how to use R for any of this, so it's not something that I'm expecting, but you are allowed to if you want to. You'll have access to the formulas just like you do in each of the assignments. There's a little pop-up with the formulas, so you'll have that, okay? And the Z table, same thing, there will be a pop-up that you can use, okay? Just like the assignment. Oh yeah, the choose function especially, you'll want to have a calculator that you know how it works, right? I'll bring scrap paper. There's a lot of quiz stuff I wanted to tell you. And just as a heads up, I am going to do assigned seating, okay? Space you out throughout the room. So just be prepared for that, okay? I thought, hey, that's what I should be doing. So that's what I am doing. P to the power of k, where P is the probability of success, right? And then I use Q, which is 1 minus P, right? The probability of failure to the power of however many failures I have, right? Q is 1 minus P, the probability of failure. The conditions for the binomial distribution, we're going to use those conditions for the rest of the distributions as well. So let's just remind ourselves what they are. So the conditions for the binomial the first is that each outcome is independent, which means that the probability of success stays the same for each trial. Okay. So each outcome is independent. Therefore, the probability of success is the same for each trial. And two, we can only have two possible outcomes, right? Yes, no, success, failure, right? That kind of thing. Only two possible outcomes. Success, failure, for example, is usually how we generalize it. Yeah. Good. Now, this formula is handy, especially if we are looking to find the probability of 4 successes in 10 trials, for example, right? Then we would use this formula, right? Even if we wanted to find, so I do 10 trials of rolling a die, and let's say rolling a 1 is a success, right? Then I can find the probability of things like at least 2 1s, right? Then what would I do? I would take the complement of that, right? And I would find, okay, 0 or 1 and subtract it from 1, right? So those tricks that we talked about last day. So we can solve a lot of problems with the binomial, right? Assuming that these conditions are met. Okay. Where we run into trouble is, what if I want to see in 100 trials, right? So I roll a die 100 times. What's the probability of at least, or let's make it easier, less than 40 ones? What would you have to do, right? You would have to say, okay, less than 40, that's 0 or 1 or 2 or 3 or 4 or 5, all the way up to 40. Each of those would it be one of these calculations. That sounds terrible, right? We're not going to do that, right? And so that's where the normal approximation comes in. Okay, so consider rolling a die 100 times. And then we need to find the probability of less than 46 ones. I'll say, and then trying to find the probability of observing less than 40 ones. Okay. We could say that the probability of less than 40, or let's use some proper notation, probability that X is less than 40 is the probability that X equals 0 plus the probability that X equals 1 plus all the way up to the probability that X equals 39, because it's not including 40, right? Each of these would be a binomial calculation, and that's going to be hard work, right? That's 40 calculations, so no thank you, right? But instead, we will be able to solve these. We will be able to solve this type of problem using the normal approximation to the binomial. Approximation to the binomial. Oops. So normal, the normal distribution, we know that. We can find probabilities associated with Z scores, right? Using the Z table or using R, more likely in real life. But for us, we'll use the Z table. Yeah. So the normal approximation to the binomial lets us say, okay, assuming that our number of trials that we're looking at is large enough, and there's going to be a threshold for what's large enough, then we can say, okay, by this crazy, I don't know what happens, well, I do, but convergence, then the binomial tends towards a normal distribution. Okay? So then all we need is the mean and the standard deviation, right? So to me, that's kind of crazy. I can take this success failure outcome, right? And then I can model it with a normal distribution. I know, it's wild, right? But then we can find the mean of a binomial. The mean is often called the expected value. So it's the expected number of successes. Okay. So here, the mean is called the expected value. So in this case, the expected number of successes. Yeah. Yeah. So if I tell you that the probability of success is 0.2 and I do 10 trials, right? How many successes are you expecting? You would expect 2, right? Which is 10 times 0.2. So that's where it's coming from. And so we can use that as the mean of our normal distribution, which means that we need to find the standard deviation, right? Because we remember that z-scores, okay, that's my gateway to using the z-table and finding these probabilities that I want, right? And so then I need the standard deviation, right? X minus mu over sigma. So then the standard deviation here, I usually use, instead of 1 minus p, because I find that it makes it look pretty messy, I just use q. So you could use, the square root of npq instead, and that's what I'll be writing. Right. And I only want to emphasize the q because later on in future chapters, we'll use the q again, the p and the q. So it's good to get in the habit of using those two. Okay. The binomial distribution with the probability of success p is nearly normal when the sample size n is sufficiently large. And here's the condition that n times p and n times q are both at least 10. So then is nearly normal when the sample size n is sufficiently large that n times p, we've seen n times p, it's the mean, right? It's the expected number of successes, right? If I take n times q, that's going to be the expected number of failures, right? And so really what we're saying is, as long as I have a sample size large enough, right, that I'm expecting at least 10 successes and at least 10 failures, then I'm good to go. Now, the thing is, whenever I ask you to use the normal approximation to the binomial, these conditions will be satisfied, but you still have to show me that you remember that you have to do it, okay? So these will check out and they will be fine, right? But we still have to do it. Okay? The idea here is that if your P or your Q is really, really small, right? So if the probability of success or vice versa, failure, it doesn't matter, right? Is really, really small, you would need a large sample size to make up for that, right? To be able to see a success, right? If the probability of success is 0.0001, right? Then you're gonna need a really, really large sample size in order to get 10 successes, right? An expected number of successes. Otherwise, there's nothing really to go off of. Right? So that's why we have that in place. Okay. And so the condition is that n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. Right? This is the expected number of successes and this is the expected number of failures. As long as that checks out, then we can use the normal approximation to the binomial. So the approximate normal distribution has parameters corresponding to the mean and standard deviation of the binomial. So this we can always find, but we haven't been because I save it for this normal approximation. So we know the mean, and then the standard deviation is just going to be the square root of NPQ. So this example is my favorite example for this, because there's no way you would want to solve it by hand. And I think it's pretty cute. Cute. Let's see here. Oh, you know what? Maybe I'll grab just a chunk to start off with. Okay. Suppose that Canadian Blood Services anticipates the need for at least 1,850 units of O-negative blood for a particular region this year. It estimates that it will collect blood from 32,000 donors, and only about 6% of people have O-negative blood. Yeah. So here, eventually what we're going to solve, give you a sneak preview, is this one. How likely is Canadian Blood Services to meet its need of at least 1,850 units of O-negative blood? How would you, right? At least 1,850. Well, you could use the complement trick, but that means you'd still have to figure out what's the probability of 0 O-negative, 1 O-negative, 2, 3, 4, all the way up to 1,849. No, thank you. Right. So we're going to work through this, and I kind of hold your hand throughout till we get there. Okay, but that is what we're working towards. But first, let's figure out what is a success, right? What are we talking about in terms of a success? In this case, it's having a donor that has O-negative blood, right? And so here, a donor with O-negative blood. What are N and P in this case? N gets a little tricky, right? Because I have a number here and I have a number here, right? But what I want you to think about is N is the number of times that I tried to get a success, right? So N is going to be this overall number of donors, right? Then the value that I want to find a probability associated with later is this 1,850, right? But the number of times that I tried to get an O-negative is 32,000. So N is 32,000. P in this case, right, the probability of success is 0.06. What's something we're not talking about? We haven't checked the independence condition, right? There are only 2 possible outcomes. So let's, I just remember, I do check the assumptions later, but let's just tackle the independence one right now, right? I'm going to have to assume that each donor is independent of the next. That's not necessarily the case, right? Because O-negative blood is genetic, right? And so if your parents give blood, you're more likely to give blood, right? So it's not true, but we are assuming that each of the donors are independent of each other, right? So that's something that we're assuming. And I'll write that down, but I remembered I do have a part that gets us to say that, so I'll save it. But that is something to think about. So then what's the mean and the standard deviation of this distribution? So the mean is n times p, right? So the mean is 32,000 times 0.06. I'll confirm, but if memory serves me, 1,920. The next one, I'm trying to remember, it's a decimal, 42.48 something. Sigma is the square root of NPQ. Which is the square root of 32,000 times 0.06 times 0.94. Don't forget that square root. 32,000 times 0.06 times 0.94. And then square root that. I nearly forgot. I'm going to round to 4 decimal places, 42.4829. Just given the mean and the standard deviation, do you feel good about them meeting this quota? I feel pretty good, right? We need 1,850. I am expecting 1,920. So right off the bat, I'm feeling pretty good, right? And even if I go down 1 standard deviation, 2 standard deviations, I get a little short, right? But that's what we're going to be talking about, right? And so remember the 68, 95, 99.7 rule. If I move 2 standard deviations away, I've covered the central 95%. Oh, it's all coming back to me, right? So far, I'm feeling pretty good about this meeting this quota, right? But we need to find the probability eventually. All right. As an exercise, I want you to set up the formula. So just set it up. I'll show you why we won't be able to solve it. So set up the formula for getting exactly 1,850 units of O negative blood. So here, let's use this here. This makes it a binomial with K equal to 1,850. Right? So if we set up the formula, the probability that X equals K is N choose K times P to the K times Q to the N minus K. Filling this in, I have 32,000 choose 1,850. P is 0.06 to the power of 1,850 times 0.94, 32,000 minus 1,850 to the power of 30,150. I've set it up, and that's as far as we can go. Right. I think on this calculator, it gives me math error, and on this calculator, I did it earlier, right? I use the choose function, 32,000 choose 1,850, it's saying, I don't want to do that, undefined. So usually it doesn't want to do that. Why doesn't it want to do that? What are we asking it to do essentially? We're asking it to make a tree with 32,000 layers and then figure out how many ways can there be exactly 1,850 successes. It's a lot. All right. So it doesn't want to do that, and that's okay. All right. I know, right? They're like, not today. Use the normal approximation, thanks. Which is what we're gonna do, right? So this most calculators. Good question. I'll have to try it because you could use the P binom. I don't know. I haven't tried. But most calculators can't handle this. I don't think you can handle this. Because it's too large. Right? And that's okay. Something makes me think that R is going to use an approximation, and it is going to use the normal approximation with some adjustments. I think they wouldn't use the choose function anymore. Okay. But the question said set up the formula, and that we did. So we're good. All right. But that's exactly 1,850. And we're working towards at least 1,850. But before we do that, let's check the assumptions. So check the assumptions for the normal approximation to the binomial, and in that we're going to check the conditions for just the regular binomial as well. So here, the first assumption is the one that I was talking about. We're going to assume that donors are independent of each other, right? And so we will assume, often instead of saying check the assumptions, I'll say state the assumptions. It sounds like a silly thing to kind of distinguish between, but often what we do is we have to just say, okay, well, this is not necessarily true, but we assume that the donors are independent of each other, right? Even though we could argue against it, right? But in order to proceed with the question, we have to assume that they are. So sometimes I'll say state the assumptions instead. Okay. So we will assume the donors are independent of each other. Sure.
So during the quiz, we usually have MCQs, and if we don't want to assume this, and we just click that this is not a binomial question, then
Yeah.
it usually makes it wrong, right?
Yeah,
So how
because
do we-
then later I make you use the binomial. So you basically, it's like a hoop you have to jump through. Where if I get you to do binomial calculations,
but for
the
quiz,
conditions should be met.
for the quiz.
So the assumptions will always be met, right? It's just how do you argue that they are met? So in this case, right, we could argue that they're not independent of each other. Like I said, if your siblings are donating blood, you might be going with them, right? And so then they're not independent. But then what we would do is we would say, okay, I'm just going to assume that all these donors are independent of each other. See the crux? Yeah, I know it is tricky because these assumptions, everyone says, well, that's not true. But then we're just listing the things that we're assuming. Does that make sense? And now that I see your face, I solved that problem. No, I forgot to message you about it. Anyways, I'll tell you. But not now. So It was one of those late night, I'm like, oh, I know how. So we're gonna assume that these donors are independent of each other, right? Which also means that each donor has the same probability of success, right? P equals 0.06. That one's kind of sticky, right? But we have to assume that they're independent. The second one is fine, right? We can only have two possible outcomes. And so there are only two possible outcomes. I guess maybe it's not fine, right? You can have, I can never remember what blood type I am, but I think you can be A positive, A negative, B positive, B negative, O negative, AB, I think. There's like all these different blood types. We've lumped all the ones that are not O negative into one outcome, right? A failure. So there are only two possible outcomes, right? You're either O negative or not O negative. Maybe I'll make this an arrow. Right, so we've lumped everyone else into a not O negative group. Okay. Now, in order to use the normal approximation, we just have to double check that our sample size is large enough, or the number of trials that we're looking at is large enough. So this is kind of the new one. 3, we have to check that n times p, which is 32,000 times 0.06, which we remember is 1,920. Well, that's greater than or equal to 10. Oh, that's supposed to be a check mark. Dink. All right, so that checks out. That's good. How can I find the number of failures if I didn't want to do any more calculations? That'd be 32,000 minus 1,920, right? Or 32,000 times 0.94, right? Two ways of finding the same thing, but we have to check n times q, which is 32,000 times 0.94, which is times 0.94, 30,080, which is also greater than or equal to 10. Hey, my check marks are no bueno. There we go. Yeah. Like I said, these things will check out, right? But we still have to write them down. We have to remember that that is something that we have to check.
So the only condition we added for the normal approach to the binomial is the third one?
Is this one.
1 and 2 are just the same as binomial.
Exactly. I'll do maybe something. Oh, you know what? I've got the perfect pen for this. Oh, maybe not. I thought I had like the glittery one. I'll have to set it up. Pink will have to do. Yeah. So now we've checked the conditions. These all check out. So now we are able to use the normal approximation to the binomial. But how? All right. Let's grab that last part of the question here. Wait. So how likely is really asking what's the probability? What is the probability? Right? But the rest of the sentence doesn't make sense that way, but how likely is Canadian Blood Services to meet its need of at least 1,850 units of O negative blood. Okay, so we have said, okay, we're allowed to use the normal approximation, which means I can draw a normal distribution. Start mapping out my problems here, or singular problem. So I'm going to use the normal approximation, so I can start with a normal distribution. And what I'm going to do, because it's so close, right, it's tomorrow, so I will explicitly say, use the normal approximation to find the probability of at least 1,850 units of O negative blood, for example, right? So I'll tell you when to use it. Okay? So then you're going to start with a normal distribution, and then we're going to jot down the mean and the standard deviation that we calculated earlier. Right, we found these guys, so I'll copy those. And move them around a little bit. Where does the mean go? It goes in the center. And sigma, let's just use the 4 decimal places. Yeah. So that's just from earlier. Right. If I haven't asked you to find those values, you would need to calculate them here, right? This one's guiding you through all the little bits and pieces, right? So that's where you would need to start. Okay. And now we need at least 1,850 units. So the units of O negative blood are on this number line down here, right? So 1,850, I'm just going to draw it anywhere to the left, right? As long as you're showing that it's less than the mean, that's fine. And it's just to help you visualize, right? So it's not important where it goes or anything like that. It's just to help you visualize. Okay. So then at least 1,850, well, that's going to be this area, right? It's been a little while, right, since last week that we did any normal distribution things, right? But from here, if I want to find an area under the curve, I first need to calculate the Z-score, and then I'm going to use the Z-table, right? Remember that the Z-table gives you the area to the left, so then we need to use the 1 minus, right? It's all intertwined here. So we're going to say, okay, Z, X is all here. X is X minus mu over sigma. X is always going to be the value that you're interested in, a probability around, right? Less than this, greater than this, right? And so X in this case is going to be the 1,850. Okay. So we're going to have 1,850 minus the mean, which is 1920, and the standard divided by the standard deviation, 42.4829. Okay, 1,850 minus 1920 divided by 42.4829 puts me at negative 1.64772178.9. Remember that the Z table only gives us 2 decimal places, right? So I need to round this properly to 2 decimal places. Negative 1.65 to 2 decimal places. DT decimal places.
Is that a Z or an X?
This is a Z. This is an approximately equal to. It's me being picky. But you could use an equal sign if you want. Okay, now what? We're gonna use the Z table, right? And usually what I do, just so that you have it in your notes, is I just write out exactly what I'm doing, right? And so I'm gonna say using the Z table. We find the area to the left of Z equal to negative 1.65 is, so now let's go to the table. Realized I didn't clean it up yet. So I'm on the negative Z side, remembering that the table entry, there's some terminology here, right? The table entry, these are the table entries, right? The areas to the left. So then I need to find negative 1.6 down here. So I'm gonna, use a highlighter or something like that. So that's my first portion of my Z, and then my second decimal is 5, right? So they join up to meet up negative 1.65, right? And the area here to the left is 0.0495. So I'm gonna jot that down. Is 0.0495. Which means the area to the right, which is the area that I'm interested in, is going to be 1 minus 0.0495. So which means the area to the right is 1 minus 0.0495. Which is 0.9505. Which in turn means that the probability that they meet this demand of 1,000 or at least 1,850 units is 0.9505. So therefore, the probability they get at least 1,850 units of O negative blood is 0.9505. Right. What would you have to do if you gave this to, so you work at Canadian Blood Services, you give this to your boss and they say, well, we need to increase that probability. What would you have to do? You'd have to get more donors, right? And then you would increase it. Right. Good. So that's the normal approximation to the binomial. Fun, right? No, probably not. It is fun, but I understand if you don't love it. Okay. Now we're gonna do kind of a fire drill introduction of some other distributions that we could use. Okay, we're gonna start with the geometric distribution. And remember, I only want you to be able to identify when it would be appropriate, right? And I also want to show you that well, you don't need a formula for the geometric distribution because you already know how to solve it. Okay, so let's start there. Well, what is the geometric distribution? We have the same setup as the binomial. In fact, we have the same conditions as the binomial. Okay, so the probability of success on each trial is P and some probability of failure, right? Then the probability of finding the first success in the nth trial. Okay? So the geometric distribution, so this formula here gives us the probability of finding the first success in the nth trial. Yeah? So in short, the geometric is used to find the probability of the first success happening on the nth trial. For example, right, if you roll a die 5 times, what's the probability that the first time that you see a 1, so if a 1 is a success, right, then what's the probability that the first one you see is on the 5th trial? How would you solve that? You've got the tools, but it's been a while, right? So consider, so for example, roll a die 5 times. What is the probability of rolling a 1 on the 5th trial? Without that formula, what would you do? Well, you probably have, you might say, oh, usually students look at me and start drawing the lines to see if they're on the right track. And you would be 1, 2, 3, 4, 5. Right? Trial 1, 2, 3, 4, 5. Now I'm forcing the 5th trial to be a success, which has a probability of 1 in 6. But I'm also forcing these guys to be failures, which is 5 and 6, 5 and 6, 5 and 6, 5 and 6. Right? So then I would have the probability of failure to the power of 4, right, times the probability of success. Okay? To me, that looks like this, right? The probability of failure to the power of n minus 1, right? I have to have failure, 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 all the way up to n minus 1 times, and then a success, right? So you don't need this formula. You would get there using the tools that we've already learned, right? But here, right, so in general, right, you would have Q, which is the probability of failure to the n minus 1 times P, right? N minus 1 successes, or n minus 1 failures, followed by 1 success. Technically, it's to the power of 1 here. This looks weird. There. Huh? Now the conditions are the same as for the binomial, right? So we can only have success failure situations, and we have to have independent events. Okay. the conditions for the geometric are the same as for the binomial. Okay. So I feel like I have an example. I do. A machine that produces a special type of transistor, which is a computer thing, has a 2% defective rate. The production is considered a random process where each transistor is independent of the others, which means, okay, it's either defective or not defective. So there are two possible outcomes, and we're told that these are all independent of each other. So the probability of it being defective is always 0.02, right? So here, I'm not going to write out the conditions, right? But they are checked out. We want to find what's the probability that the 10th transistor produced is the first with a defect. We could solve this, right? We could solve it just using 10 lines, right? Forcing the first one, second one, third one, fourth one, fifth one, sixth one, seventh one, eighth one, ninth one to not be defective, right? With a probability of 0.98. And then the last one has to be defective. So here for A, right, we could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.98, 0.98. Oh man. They couldn't do like 6 or something, 0.98. Until the very end, 0.02. All right. This is going to become 0.98, technically to the power of 10 minus 1, right, to the power of 9, times 0.02. Which, well, let me change the color here. Better. Which is approximately 0.01667. Stop it there. So you know how to solve that, right? So, but what I'm asking from you on the quiz is, reading that, do you know that you could model that with a geometric, right? Okay, the first transistor is the 10th one, right? The nth trial. What's the probability that the machine produces no defective transistors in a batch of 100? This isn't a geometric, right? Because the geometric tells me what's the probability that the first one happens on the nth trial, right? It's not a binomial because I don't have any successes. I guess it could be a binomial. But really what we're saying is that, okay, in a batch of 100, which is going to translate to 100 little slots, right? None of them can be defective, right? What's that probability? That's going to be 0.98 to the power of 100. So the probability of no defective in 100 is 0.98 to the power of 100. Which is roughly 0.1326. On average, how many transistors would you expect to be produced before the first with a defect? Yeah. And what's the standard deviation? So this is hinting towards if we're expecting something that's the expected value, right? And so then it's really asking for the mean. Now let's go back here and say, okay, well, the mean for the geometric, and I'll do this whole thing here. The mean we're going to find is 1 over p. And there's no easy way to kind of wrap your head around how the standard deviation comes around. So let's just accept it as fact. Okay, just go with it. Why would it be the probability of failure divided by the probability of success squared and then square rooted? I don't know. Could probably figure it out, but I don't know. But we can find the mean, which is 1 over p, which in this case, the mean or the expected number of trials before we reach the first defective, right? Because that's what the geometric tells us, is going to be 1 over 0.02. 1 divided by 0.02 is 50. We would expect to have 50 transistors come and go without defect until we see the first defect, right? That's what we're expecting. Yeah. Because P, the probability of success, which is a defective one in this case. Let me see here. Yeah, the first with a defect, which means a defect is a success. Yeah. Sigma is going to be the square root of 0.98 divided by 0.02 squared. 0.98 divided by 0.02 squared. Square root that. I get a sigma of roughly 49.4975. Quite a large standard deviation. But like I said, just reading it, and as soon as you see, okay, the first success, what's the probability that the first success happens on this trial? Geometric. Okay. How about, and I'm going to mix up the order here, the negative binomial. The negative binomial is a more general version of the geometric. Okay, and so the negative binomial describes the probability of observing the kth success, so not just the first success, but the kth success on the nth trial. Now, the added condition is that the last trial must be a success, right? We have to end it after this kth success. Yeah. So the negative binomial is a more general version of the geometric, right? It's not just the first success. Now we're talking about the kth success, right? If I'm talking about the third success on the 10th trial, then I'm allowing the first and the second successes to happen. It could be first and second, or first and third, first and fourth, right? That kind of thing. So there are going to be a number of possible outcomes, and hence the choose function in here, right? Same as the binomial, but the negative binomial is a more general version of the geometric. or rather, the geometric is a negative binomial with k equal to 1. Right? The first success on the nth trial, that's the geometric. So if I let k be 1, then I have n minus 1 choose 1 minus 1. There's only one way to choose 0 successes, right? So then this becomes 1, and then I have the exact same formula as the geometric, right? Okay. So the probability that the kth success on the nth trial, we've got this choose function, right? N minus 1, choose k minus 1, but then the p to the k and the q to the n minus k, that's familiar to us, right? That's the same as the binomial. And let's bring up the conditions for this thing. And I know that this is a lot, but if we can just say it and agree that we talked about it and check that off the list and move on with our lives, I think that'll be really nice. So I know it's stressful right now, but you got this. Okay. So the negative binomial has the same conditions as the binomial, right? So let me see here, crop, move this over here, right? So 1, 2, and 3, these are the same as the binomial. And then this one is new. The last trial must be a success. I lump 1 and 3 into 1, right? Saying that they're independent means that they're going to have the same probability, so I get lazy. Okay. I think this is where I have the example where I show you the type of question that I'm going to ask you on the quiz. I think it is. Okay. This type of question on the quiz. And I'm going to add one here, binomial or negative binomial or geometric. So the question reads, on 70% of days, a hospital admits at least one heart attack patient. On 30% of days, therefore, right, no heart attack patients are admitted. Okay. So they either get a heart attack patient or they don't, or at least one heart attack patient or they don't. Okay. Identify each case below as a binomial or negative binomial or geometric. I'm adding that. And compute the probability. I'll set it up, but we'll see if I have time. I might fill in the blanks later, right? For us, what I want us to do is just decide which of these would apply, right? So the first one, what's the probability that the hospital will admit a heart attack patient on exactly 3 days this week? Okay. Go through the list. Okay. Well, I am feeling good about it being a binomial, right? If I want to find the probability of exactly these many successes, right? Or this many successes, the binomial helps me do that, right? But let's just go through the list. The negative binomial tells me what's the probability of the kth success on the nth trial. I can't really kind of mold that to this question, so I'm going to discard it. How about the geometric? The geometric tells me the probability that the first success is on the nth trial. But now I want to have exactly 3 successes this week. In a week, how many trials do I have? I have 7, right? Each day. So this, I'm ready to commit to a binomial, right? So let's go through and figure out what types these are. And then I have the calculations that I'll probably just insert into the notes before I upload them. Okay. And I encourage you to try it, but it's not on the quiz, so I don't want to waste their time. How about B? What's the probability that the second day with a heart attack patient will be the 4th day of the week? So now all of a sudden, the second day, so that's my second success, right? Happens on the 4th trial. Okay. So let's see here. We've got the binomial doesn't really work, right? Because I need some number of trials, and then I would need to consider, okay, I could have the first heart attack day on the first day or the second day or the 3rd day, but I'm forcing the second heart attack day to be on the 4th day, right? Kind of tricky, but it is a negative binomial. Yeah. What's the probability that the 5th day of next month, which is kind of irrelevant, but I think it's there to kind of throw you off a little bit, or at least to think about it, right? You can just start, okay, that's the 5th day. Okay, the 5th day of next month will be the 1st day with a heart attack patient, right? So the first success happens on the 5th trial. Okay. That sounds like a geometric or a negative binomial with k equals 1. Okay. So this is where I do kind of a rude thing. And I'm going to just grab those calculations and paste them in. So you'll have them when I upload the notes, but I do want to talk, I need to talk about the Poisson. So there, if you wanted to try it, you can.
So both of these answers will be correct.
Yes. Yeah.
Negative binomials have an order of success, whereas just a binomial has a number of successes for a period of time.
Exactly. Yeah. Mm-hmm. The Poisson. Is the last one, and it's a little bit different than these ones, which you can kind of map the relationships, right? So I'm not going to focus too much on this. I should be, but I'm not going to. Okay. And so the Poisson distribution is when we want to count some number of events, right? And so we have some rate that they happen at. And some typical examples include defects in a piece of sheet metal, I know is one of the questions that I've used in the past, right? I'm not going to make you do it because we didn't get to talk about it, but this is what we're going to say about it, okay? So the Poisson, we need to know the rate at which these events are happening, right? I get 4 customers in a store per hour. right? For example, what's the probability of seeing 10 customers in an hour, right? So then I take my rate, which is lambda, and lambda is kind of a cutie. Yeah. So lambda is the rate of events. Then we can use the Poisson distribution to find the probability that I observe K events, right? So like I said, if I see customers in my store at a rate of 4 per hour, what's the probability that I see 10 customers, right? So then I would have 4 to the power of 10 times e to the negative 4 divided by k factorial, which is, I skipped it with the choose function. It uses the factorial. Really k or k factorial is k times k minus 1 times k minus 2, or 10 factorial would be 10 times 9 times 8 times 7 times 6. Counting down is hard, all the way up to 1. Let's leave the Poisson here. I did have an example that we could have gone through, and it might be fun to work through it, right? So for example, a coffee shop serves an average of 75 customers per hour during the morning rush. Which distribution have we studied that's most appropriate for calculating the probability of a given number of customers arriving within 1 hour during this time of day? The Poisson. And then kind of a fun fact about the Poisson is that the mean is lambda, but also the variance is lambda. So the standard deviation is the square root of lambda. But forget I said anything. No, don't worry about the Poisson, but focus on those other ones. All right. If you have any questions, let me know. Otherwise, I'll see you here tomorrow for our quiz.
I have a normal distribution question. I despise exactly this.
That's fair.
Is there a function in R or anywhere else where I can get the Z value and the probability?
I'll show you. Let me just stop this recording here.